the effect measures completely. So in order to generalize now, you're going to have to adjust for every cause of the outcome, everything that determines the risk of the outcome, not just everything that determines the effect size. That's a much bigger set of variables. The set of variables that determines effect size is a subset of those variables that are associated with the total risk. Okay. So unless the investigators have accounted for every cause of the outcome that differs between the study population and the target population, this model is not an accurate approximation of the data generating mechanism, and it will lead to invalid inferences. That is, as I just said, in contrast to approaches based on conditional effect measure homogeneity, where it would have been sufficient to account for everything that determines effect size. So just to reinforce why I think this shift in focus from effect homogeneity and measure to effect homogeneity and distribution has been a radical change, let me try and explain this in terms of an attempt to generalize knowledge about the effect of homeopathy. So suppose we've done a randomized trial on the effect of homeopathy versus no treatment in men, and we've concluded there's no effect. Now we want to know what will happen to women if they get homeopathy. The problem here is that if we're relying on effect homogeneity and distribution as our way of operationalizing effect homogeneity, and if we believe there are causes of heart disease that differ between men and women, we're forced to conclude that we cannot say anything at all about how homeopathy will affect women. In contrast, if we use an approach based on effect homogeneity and measure, we can instead try to account for every covariate that's associated with the effect size, the magnitude of the effect of homeopathy. And that seems like a much more tractable problem. So another reason why effect homogeneity and distribution is a very strong concept, too strong in my opinion, is that if we genuinely believe there's effect homogeneity and distribution, it means we can do the meta-analysis separately in the placebo arm from the active arm. Do one meta-analysis in the placebo arm, another meta-analysis in the active arm. I think that throws away randomization, and it's going to lead us the wrong way. So this is the approach to effect homogeneity that is currently receiving a lot of grant funding, a lot of attention, a lot of publications. This is where the entire methodological community has gone. It's gone this way of operationalizing effect homogeneity in terms of counterfactual distributions and throwing away effect measures completely. So what I'm trying to do is provide a new definition of effect homogeneity, which allows us to retain the idea of controlling only for those things that are associated with the magnitude of the effect, but give a biological interpretation to the magnitude of the effect and overcome those problems that made the original attempts to define homogeneity in that way. Try to overcome those problems that limited their applicability without having to go all the way down to effect homogeneity and distribution, because I want to retain the ability to only control for the things that are associated with treatment response, not with all of the things associated with the risk. Okay, so for that reason, I introduced a new effect measure called counterfactual outcome state transition parameters. What that is they are the outcome switching probabilities that you observe, that you see in response to treatment. If I'm someone who would have died if I don't take the drug, what's the probability that the drug saves me? If I'm someone who would have survived if I don't take the drug, what's the probability that the drug kills me? Those are two probabilities that are operating in opposite directions. One that says something about the beneficial effect of the drug, and another that says something about the harmful effect of the drug. I call them G and H. Okay. Then I define effect homogeneity in terms of the parameters G and H. So I'm saying if the probability that your outcome is altered because you took the treatment, if that probability is equal between men and women, then the effect is equal. That's a new definition of effect homogeneity. And it can be written as the counterfactual YA1, that is, the outcome if you take the drug is independent of which population you're in, given what happens if you don't take the drug. If we define effect homogeneity in that way, we resolve every major shortcoming of the standard effect measures. The underlying parameters are symmetric to the coding of the outcome. They are collapsible. They have no zero constraints. They do not make predictions outside of valid probabilities, and they're not baseline risk dependent. They also have a biological interpretation, which I discuss in detail in my paper. So this definition of effect homogeneity does have one major drawback, and that is that the counterfactual outcome state transition parameters cannot be calculated even from a perfect randomized trial without further assumptions. And a lot of people stop listening at this stage because they consider identifiability of the effect parameter to be key, and that's a fair criticism. But if you keep listening, I will try to demonstrate to you anyways that these unobservable effect parameters can still be useful as a bridge between the background biological knowledge on the one side and homogeneity of observable standard effect parameters like the risk ratio on the other side. That's where I'm going with this. Okay, but if we did want to identify the effect on the counterfactual outcome state transition parameter scale, if you wanted to calculate the value of those parameters from the data, the assumption that we would have needed would be monotonicity. What that means is that the drug only operates in one direction. If we have a drug that is on average harmful, then that drug would be monotonic if that drug doesn't also help someone. You could be unaffected by the drug, but as long as there doesn't exist both individuals who are harmed and individuals who are helped by taking it, then the effects of that drug is monotonic. So whether monotonicity is a plausible assumption really depends on what setting you're in. For example, there will be a lot of drugs where we have some kind of rare side effect that has nothing to do with whatever the drug is being used to treat. And it would seem very unlikely that anyone are actually cured or anyone are actually prevented from having that side effect by taking the drug that is causing it. Okay, so as a concrete example, if we're talking about the antiarrhythmic drug amiodarone, then if we're talking about the outcome of arrhythmia, then there will be some people who actually are prevented from having arrhythmia by the drug, but also some people who get arrhythmia because of the drug. So the effects are not monotonic for that outcome. But they could still be monotonic for the side effects of the drug, like pulmonary fibrosis. It's very unlikely that amiodarone prevents anyone from getting pulmonary fibrosis, and therefore the effects are monotonic for that outcome. And then it might be suitable, then it might be appropriate to use the counterfactual outcome state transition parameter scale. So one thing to keep in mind is that if the drug only operates in one direction, then one of the counterfactual outcome state transition parameters is going to be equal to 1. And then the other one can be calculated from the data. Okay. So here are my identifiability results. Basically what we're showing is that if treatment monotonically reduces the incidence of an outcome, then the counterfactual outcome state transition parameter G can be identified from the data of a randomized trial and is equal to the standard risk ratio. If treatment monotonically reduces the incidence of the outcome and the effects are equal in the sense defined in this paper, then the risk ratio in the study population will be equal to the risk ratio in the target population. Now I've moved to my unobservable counterfactual outcome state transition parameters to the standard effect measure scales, the standard observable risk ratio. So, I've given you a justification for using the risk ratio scale in terms of an underlying causal model. Okay. Now, it might be that the effects of the drug are not monotonic. If so, then the risk ratio in the study population is a biased estimate of the risk ratio in the target population. So we give you results on the direction and magnitude of that bias as a function of how much non-monotonicity there is, and as a function of the differences in baseline risk between the study population and the target populations. Okay, so these were results for drugs that reduce the risk of the outcome. If we instead have a drug that increases the risk of the outcome, you would get similar results for the counterfactual outcome state transition parameter H, but instead of identifying the normal risk ratio, you would apply them to the recoded risk ratio, the one for the probability of surviving, sometimes called the survival ratio. So the direction we're going in is to claim that you should be using the normal risk ratio for drugs that reduce the incidence of the outcome you're interested in, and the survival ratio for things that increase the incidence of the outcome you're interested in, and that will constrain the risk ratio between 0 and 1. So unfortunately, counterfactual outcome state transition parameters are not symmetric to the coding of the exposure variable. So in other words, instead of using the definition that what happens if you take the drug is independent of your population given what happens if you don't take the drug, we could be thinking about this the other way around. As what happens if you don't take the drug is independent of the population you're in given what happens if you take the drug. That would have led to exactly the opposite results of what I showed you on the previous slide. So we will refer to the first condition as equality of the effect of introducing treatment, and the second condition as equality of the effect of removing treatment from a fully treated population. And one thing that I'm not going to go into in this presentation is that I can give you biological models, a formal causal model, based on a priori knowledge of evolutionary mechanisms that support equality of the effect of introducing drugs over equality of the effect of removing treatment. As a broad overview of the kind of thinking that this argument is based on, what's going on there is that we think about unmeasured cofactors which determine whether treatment has an effect or not. And we show that if they interact with treatment according to the kind of mechanisms that would cause equality of the effect of introducing treatment, it will be easier to construct an evolutionary model in which that covariate becomes stable than it will be to construct a setting where you get the equality of the effect of removing treatment. Okay. So I'm telling you the predictions of my model, if equality of the effect of introducing treatment is more reasonable than equality of the effect of removing treatment, you will see more homogeneity observably on the normal risk ratio scale if treatment reduces the incidence, and more homogeneity on the survival ratio scale for drugs that increase the risk for side effects. Now, interestingly, this is something that John Deeks showed empirically in 2002. Published that in Statistics in Medicine. And I did not know that when I made this model. And in many ways, what I'm doing can be understood as a theoretical explanation for the findings that Deeks got in 2002, and which also led to the Cochrane collaboration recommending that we use the normal risk ratio for things that decrease the incidence and the recoded risk ratio for things that increase the incidence. You can find that recommendation in chapter 9.4.4 of the Cochrane Handbook, but it's not something that anyone does in practice. Everyone just uses the normal risk ratio for everything, even if the drug increases the risk. So that's why I'm saying we should be doing things differently. And to explain a little bit about what will